From the second you wake up to the moment you fall asleep, it's there. It's powering our homes, our cities, and yeah, the very device you might be watching this on. It's this invisible force that is, well, it's absolutely everywhere. So in this explainer, we're going to pull back the curtain on the incredible story of electricity.
Okay, so this sounds like the start of a pretty weird riddle, doesn't it? You've got this supercomputer in your pocket, a huge, spectacular display of nature's raw power, and a fossilized chunk of tree resin. I mean, they seem totally unrelated, but believe it or not, they're all connected by one single fundamental idea.
Yep, that's it. The answer is electricity. It's the invisible thread that ties the ancient world directly to our own. So we're going to go on a little journey here, starting with a curious observation from thousands of years ago, all the way to the super sophisticated tools we use today to measure and control this incredible force. To really get a grip on electricity, we've got to hop in our time machine and go way, way back. Long before light bulbs, before power grids, our story kicks off with a simple, almost magical-seeming observation in ancient Greece.
Just try to picture this for a second. You're a philosopher in ancient Greece, a guy named Thales of Miletus, and you're just casually rubbing a piece of amber. All of a sudden, you see it start pulling little bits of fluff and feathers towards it, like magic. He had no clue what he was seeing, but he was the very first person we know of to write down the effects of static electricity.
And here's the really cool part, the little bit of trivia. That one simple observation gave this whole field its name. See, the Greek word for amber is electron. And from that single ancient word, we get electron, electronic, and of course, electricity. It literally all started with fossilized tree sap. How cool is that?
For centuries, that weird property of amber was just a curiosity. Kind of like a cool party trick, but not much more. To get from that party trick to powering the entire planet, we first had to figure out the invisible rules that were actually at play.
So, the field of science that explains what Thales saw, it's called electrostatics. It's all about what electric charges do when they're sitting still. That's the static in static electricity. And this is where we need to zoom in and look at the fundamental building blocks of, well, everything.
So here's the deal. Everything is made of atoms, and atoms are made of even smaller bits with different charges. You've got your positive protons locked in the center, and these zippy negative electrons orbiting around them. Normally, it's all perfectly balanced, so the atom is neutral. But when you rub that piece of amber, you're physically knocking some of those electrons loose, and that creates an imbalance of charge.
And this right here, this is the one rule to rule them all. Seriously, this is the fundamental law of the universe when it comes to electricity. Opposites attract, and things that are the same repel each other. That charge imbalance we just talked about on the amber, that's what created the force that pulled those feathers toward it. This one simple idea governs everything, from static cling on your laundry to how our entire power grid works.
All right, let's do a quick whirlwind tour through history and see how we went from that basic principle to actually harnessing this incredible power. It took centuries, with brilliant minds all building on each other's work.
Okay, so we start with Thales and his amber. Then, bam, we fast forward over 2,000 years to Benjamin Franklin flying a kite in a storm, who proved that lightning was just a giant spark of electricity. Game changer. Then, in 1800, Alessandro Volta gives us the first battery, a way to store and use electricity whenever we want. Not long after, Michael Faraday figures out how to make electricity using magnets, which is the basis for pretty much all modern power plants. And finally, Nikola Tesla develops the AC system that actually powers our world today, making it possible to send electricity over long distances. What an absolutely incredible relay race of discovery.
And that brings us right up to the modern era. We don't just, observe electricity anymore. We measure it with incredible, pinpoint precision. And to do that, you need the right tools.
I mean, just look at the difference here. On the left, you've got this old-school analog meter with a physical needle. It worked, sure, but you had to kind of squint and hope you were reading it right. And on the right, a modern digital multimeter. It's got a bright, clear screen, it's super precise, and it's packed with functions. It's the perfect symbol of how far we've come.
This little device, the multimeter, is basically the Swiss Army knife for anyone who works with electricity. And like the name suggests, it's a multimeter. It combines a bunch of different measurement tools into one handy gadget. It lets us actually see the invisible by measuring voltage, current, and resistance.
Okay, so how does this thing actually work? Let's break down the three main jobs a multimeter can do. This is how we put numbers to the invisible force that runs our modern world.
First up, we've got voltage, measured in, you guessed it, volts. The absolute best way to think about voltage is to think of it as electrical pressure, right? Just like water pressure in a hose, voltage is the push, the force that gets the electric charge moving through a wire. The battery in this circuit, that's the pump, providing the pressure.
So to measure that pressure, you just turn the dial to the V setting. Then, and this is important, you connect your probes in parallel. That just means you touch the two probes across the component you're testing, without actually breaking the circuit. It's exactly like attaching a pressure gauge to the outside of a pipe to see what the pressure is inside.
Next up is current, which we measure in amperes, or just amps. So if voltage is the pressure pushing the water, then current is the actual flow rate. It's how much water, or in our case electricity, is actually moving through the pipe per second.
Now, listen up, because this is totally different. To measure the flow, you have to put your meter right in the path of the flow. You select the A setting on your dial, but then you have to physically open up the circuit and connect your meter in series. This way, all the current has to flow through the meter for it to be measured.
And last but not least, we have resistance, measured in ohms. Resistance is, well, it's exactly what it sounds like. It's how much something fights back or resists the flow of current. A really thin wire has more resistance than a thick one, just like it's a lot harder to push water through a tiny straw than a fire hose.
To measure resistance, you turn the dial to that little omega symbol. And just like with voltage, you connect your probes in parallel, across the component. But, and this is a huge critical safety tip, the circuit absolutely must be powered off. You can't measure resistance while electricity is trying to flow through it.
So there you have it. What a trip, right? We've gone from Thales of Miletus rubbing a piece of amber in ancient Greece to understanding the fundamental forces of attraction and repulsion, and finally, to using a digital tool to precisely measure the voltage, current, and resistance that bring all of our technology to life.
It's really just an incredible story of human curiosity. We took this subtle, mysterious force of nature and we turned it into the bedrock of our entire civilization. It kind of makes you wonder, doesn't it? What other invisible forces are out there, just waiting for us to discover them, measure them, and maybe, just maybe, master them next?